Scientific measurements. We record scientific measurements in a very precise way so that each of the digits that we record is certain except for the last one. And the last one is always estimated. So, examples. I had trouble with examples yesterday. So if I wrote 12.5 feet, when a scientist writes that, we mean that this is 12 feet. There's no question about that. And then we're estimating, we think it's roughly halfway between 12 and 13. But the 5 is estimated. If someone else measured perhaps this board, they might find out it's 12.4 feet or something. And that's okay. But we always estimate the last digit. When we look at this data here on carbon monoxide concentrations in parts per million, in this table it's listed as 8.9. That says we're certain of the 8 and we're estimating the 0.9. In this table over here, these numbers, 9, that says there's only the one digit. The one digit is the last digit, therefore it's estimated. So the 9 itself is an estimate. That suggests to me that it's between 8 and 10. So this number is just an estimate, really. And this number gives me a lot more confidence that it was measured more carefully. And we always express our measurements based on the device that we made them with, so that we communicate to other people that, oh, this is an estimate, or no, I measured this very precisely. The distance from my house to Fresno City College is about 30 miles. So if I was going to write that, I would write 30 miles. And this would, I'd be certain of the 30, it's, 30 something. This next one, I don't know exactly. I don't see any point in measuring it exactly. If I did measure it exactly, I might say it's 31.143 miles. And that would imply that I had measured very carefully and I was just estimating this digit. So the last digit's always estimated. Let's look at some measuring devices and see how this works. The number of digits that get reported depends on the instrument that you use. And some instruments give much more information than others. Here we have a pistachio on a typical kitchen scale. So here we have ounces on the left and grams. We're in science class, so we're going to look at grams, not ounces. If you look at this, the black line is one that moves. The more you press down on the balance, the farther down the black line goes. And we see here that it is definitely after that first little red mark and before the next one. Well, we need to look at these and figure out what do those marks mean. This one's labeled 0 and this one's labeled 10. So we look at the divisions in between. There's 10 divisions. They must each be 1 gram, right? So when we look at that, is there any question that this pistachio weighs at least 1 gram? No. It clearly weighs a little bit more. So we report 1 gram, and then we estimate the next digit. So here we've got the 1 gram, and that's in the ones place. So the next decimal place will be estimated. That's where we take our best guess. We estimate. So you look at that and you imagine 10 divisions in between, and you might say, oh, I think it's 1.2 grams. Your neighbor might say, no, that's 1.3. Somebody else might say, I think it's 1.1. We're not going to argue about it. It's an estimate. We call this reading between the lines. And I'm going to get on you about this in lab because we're going to be using rulers and graduated cylinders and burettes and things, and we need to read between the lines. Yes?
So do you want us to put our guess plus, like that one says 1 and then 1.2? So do you want us to have 2 answers?
No, I just want the 1.2. This is saying that the markings are every 1 gram, and so we record the reading as 1.2 because the divisions are 1 gram. We estimate the tenths. Let's look at a couple other examples. Here's a thermometer. The question is asking us to record the measurements with the correct number of digits. So here's the red alcohol in here. They didn't do a great job here. It's kind of hiding behind the 100, but it's in here somewhere, right? Well, let's first think about the thermometer and its divisions and find out, what does the smallest division represent? What does each of these little black lines represent? 1 degree. Now, we can't really tell if this is Fahrenheit or Celsius, but we're in chemistry class, so it's probably Celsius. So the markings are 1 degree Celsius. That means we estimate to the 10th. So if we look at that, we can see that it's 103 and a little bit. So it's definitely 103. There's no question about the ones place. There's markings. We're looking at the lines. Now we read between the lines, and that's where the estimate comes in. What do you think it is? 0.1. 103.1 degrees Celsius. Others might disagree, but that's okay. The 103 will be the same for everybody. The point something will vary. Any questions? Let's look at this graduated cylinder. When you put a liquid into a graduated cylinder or any sort of a narrowish cylinder, there's a curve in the surface of the liquid. We'll talk later in the semester about what causes that. But it's called a meniscus. And what we do is we always measure to the bottom of the meniscus. We need to do that because that's how the glassware was calibrated. So the bottom of the meniscus is right in here. Well, let's look at this. Here we've got 4 and 5. So each of these white lines represents what? 0.1. So here are the markings are 0.1. What do you think the units on that are? It doesn't give us the units. Probably milliliters. We'll just say it's milliliters. The markings give us 0.1. That means we need to estimate the next digit. So that's tenths. We need to estimate the hundredths. So we look at this, and we've got 4.5. It's between 4.5 and 4.6. So 4.4, there's no uncertainty in that. What do you think the next digit is? Somebody over here says 9. That's fine. Yeah. I'm sorry. 4.5. Where do these things come from? Or you might think it's 4.58. I wish I could say I did those things to see if people are paying attention, but that's not. Thank you. I appreciate that. We'll just play along. Just keep the teacher happy. Any questions? This brings us to significant figures. Oh, question. Can I go to the restroom? Absolutely. Thank you. Anytime. You need to get up for any reason. Just do it quietly. I've had people in the past who just had a hard time either sitting still or staying awake when they sat still. And so if you need to pace in the back of the room, I am fine with that. Just try not to disturb others. Sig figs. You guys heard of sig figs? Done sig figs before? How many of you hated sig figs? Yeah. Not too many of you loved them, probably. Sig figs are sort of a necessary, they're not evil, but the alternative is differential calculus. So I think sig figs are easier, so we'll just get by with them. So the precision of a measurement depends on the instrument. We just talked about how to record the measurements correctly. When we do calculations with those measurements, we need to preserve that amount of precision. And so we use significant figures to help us with that. Significant figures, sometimes called significant digits, are the non-place-holding digits in a measurement. So in a measurement, they include all of the certain digits that we recorded and that first estimated digit. So the greater the number of significant figures a measurement has, the greater the certainty or precision of it is. So we have a set of rules for counting significant figures. Any digit that's not 0 is a significant figure. And these columns show examples of that particular rule. So here, the 1, the 3, and the 1 are non-zero digits. This 0 isn't bolded because it's a 0. 0 is not a non-zero digit. Anyway, so here we've got the 4 and the 2 and the 1. It's the zeros that are the problem. Interior zeros. Zeros that are squeezed between non-zero digits are significant. Here we have an interior 0. It's between 4 and 3. In this number, there are 2 interior digits because they're on the inside of the number. Those are always counted as significant. Then we have leading zeros. Leading zeros lead the number. They come at the beginning of the number. They are never significant. The only reason we write zeros at the beginning of a number is to hold the decimal place. Now, if I measured something and it was 1.5 centimeters, and I wrote 2 zeros at the beginning, it looks weird, but does that change the value of the number? No. So if I could write 2 zeros, I could write 500 zeros if I wanted to. We're not going to count these as significant figures because they don't reflect measurement, and they're really not needed. In numbers like this, though, 0.00023, if we don't have those zeros, the value of the number changes. The zeros are necessary. They're important, but they don't reflect measurement. They're just there to hold the decimal place. The thing about non-significant zeros is they go away when you put a number in scientific notation. If we put this number into scientific notation, we're going to take this decimal point and we're going to move it 1, 2, 3, 4 places. So it's after that 2. This would then be 2.3 times 10 to the minus 4. This is a negative number because this is a small number. If your original number is small, the exponent is negative. I have negative feelings about small paychecks. If it's a positive exponent, that means it was a large number. Now we don't need those leading zeros anymore because the power of 10 here holds the decimal point for us. So leading zeros never get counted. Here's another number with some leading zeros. Then we have trailing zeros. Those are the ones that come at the end. The rules I'm giving you here are slightly different than the way your book explains it. It gives the same result. This makes more sense to me. If you like the book rules, go ahead and use them. Trailing zeros are significant if there's a decimal point written in the number. It actually has to be written. Where's that word? Written. So here we have 39.0. That's a trailing zero, but there's a decimal point. So we count that as a significant figure. 120.00. The decimal point tells us that those trailing zeros are significant. In 39.0, would the value of the number change if we didn't write the 0? No. It's not there just to hold a decimal place. It's there to reflect measurement. It's an estimated digit, but it's a significant digit. What if there's no decimal point? Trailing zeros with an implied decimal point are ambiguous. They should be avoided. So this number 300, we have 2 trailing zeros. The decimal point is not written. We know where to put it if they said put a decimal point in that number after the last 0. But we don't normally put a decimal point there because it's not really needed. If we lost those 2 zeros, the value of the number would change, wouldn't it? 3 and 300 are not at all the same. But we're not sure if the writer of that number meant 300 to the nearest 1, 300 to the nearest 10, or 300 to the nearest 100. It's ambiguous. Ambiguity is not good in science. So what we do if we're pressed to answer how many significant figures in 300, 300, we'll assume the worst case, the lowest precision, the worst uncertainty, and we'll say, well, those are uncertain, and that the writer means 300 to the nearest 100. So between 200 and 400, really just an estimate. Here's another example, 238,100. We're not sure if these are actually reflecting measurement or not. So we'll assume that they aren't. And we would say that this number has 1, 2, 3, 4 significant figures. 100,000, as written, how many significant figures? Just the one. Any questions? Yes?
So if you put 0.0 after any of those, then that would be all significant, right?
Right.
The first three.
Yeah, so 100,000, and put a decimal point there. A scientist understands that that just made all the zeros significant, and that was measured to the nearest one. That's not the best way to write the number, though. And what if you want to indicate that it's to the nearest 100? How do you do that? Well, you can do this. Underline it. That's something we use in chemistry kind of in our notes. That's not 100, that's 1,000, sorry. This is 100. But that's not universally understood. If we want to indicate that this number is estimated to the nearest 100, then what we're going to do is we're going to put the number in scientific notation. So this would be 1.000 times 10 to the 5. In scientific notation, this coefficient is always at least 1 or greater. There will never be leading zeros in scientific notation. And if there are any trailing zeros, there will always be a decimal point. The nice thing about scientific notation is you don't have to worry about the zeros. Anything in the coefficient is a significant figure. Yes?
Why did you put 3 zeros as opposed to 2?
Well, I'm trying to indicate, as I did here, that the uncertainty lies here. And so I'm including this 0, and this 0. I'm not including those two because I'm saying those are just holding the decimal place. In scientific notation, now this exponent holds the decimal place for me. We'll get some practice with this in lab today when we do the worksheet. Then we have exact numbers. We treat exact numbers as if they had an unlimited number of significant figures. How many fingers am I holding up? 2. Is there any uncertainty in that? No, it's exactly 2. We could say it's 2.00000. You could say 0 forever. Exact. So when we count discrete objects, we have an exact number. We could count the number of people in the room. It would be an exact number. Another example of an exact number is integral numbers that are part of an equation. Integral means integer here, whole numbers. The volume of a sphere is 4/3 pi r cubed. The 4 and the 3 are exact numbers. The other situation is defined quantities. How many inches in a foot? 12. Is there any uncertainty in that? No, because the foot is defined as 12 inches. When you're within the metric system, all of the length units, those conversions will be exact because they are by definition. Within the English system, everything's exact because it's defined. Where you want to run into trouble is when you go back and forth. So there's one exception that I want you to know. 1 inch is exactly equal to 2.54 centimeters. That's one of the unusual conversion factors between metric and English that is an exact number. When we find an exact number in a calculation, we'll find that it's not going to alter the number of significant figures. So let's practice counting sig figs. 554 kilometers. How many significant figures? I heard 3. Sometimes we're tempted to say it's infinite because it's a whole number. But it's a measurement. It's not counting. You can't count kilometers. They're not objects. 1.01 times 10 to the 5th meters. 3. In scientific notation, all of the digits in this coefficient part are going to be significant. That's an interior 0, so we're going to count it. 1.4500 kilometers. 5. We have trailing zeros, but there's a written decimal point, so they count. 7 pennies. I heard 1 and I heard infinite. Those are a little bit different. Can we count 7 pennies and be certain? Yeah. So we would say this is an infinite number of significant figures because it's a counting number. 0.00099 seconds. 2. These zeros at the beginning are just holding the decimal place. They don't reflect measurement. So we just count the 9 and the 9. 21,000 meters. 2. There's no written decimal point. It's only implied. So we're going to assume the worst and say that these trailing zeros are just placeholders. Yes?
Can you explain further D?
D, the 7 pennies?
Infinite.
Because there's no uncertainty. So here's 1 penny, 2 pennies, 3 pennies, 4 pennies, 5 pennies, 6 pennies, 7 pennies. Is there any uncertainty in how many purple circles I drew on the board? No. So where's the uncertain digit in 7?
There's none.
There isn't one. It's exact. So if we say there's 7, the last digit in a measurement is always uncertain. So then we'd say, well, 7.0, and we could just keep writing zeros. And we're never going to get to an uncertain digit because there's no uncertainty.
All right.
So instead of messing around with stuff like that, we say, oh, it's infinite.
All right. Thank you.
You're welcome.
Can you further explain
E. Yes. So 0.00099 seconds. These zeros are very important, but they're not what's called a significant figure. One of the things that can help us unveil those non-significant zeros is putting numbers in scientific notation. So if we put this in scientific notation, we're going to move the decimal point 1, 2, 3, 4 places. It's going to be 9.9 times 10 to the exponent is a 4. We look at this number, it's a small number. Mrs. K has negative feelings for small paychecks, so this is a negative exponent. And then we need the unit.
So as long as we can write it into scientific notation and count it that way, we should be fine.
Pretty much, yeah. Put it in scientific notation. You still have to have some understanding, though. The leading zeros, yeah, put it in scientific notation, they'll disappear, you'll be happy. But here, the 21,000 or the 1.4500, here you could put it in scientific notation and you could do the wrong thing with the zeros. So that is a little dangerous. Any other questions? When we have calculations with measured quantities, we shouldn't gain or lose precision just by multiplying or dividing. So we have rules. We count the sig figs, and then we apply these rules when we do the calculations. And yes, I know I'm going over, but we really need to finish this. So in multiplication or division, those are related operations in math, and they use the same rule. The result has the same number of significant figures as the factor with the fewest significant figures. I've been using these slides for quite a while, and this figure here is straight out of the textbook. And yesterday someone pointed out to me that this result is actually wrong. So, you know, I never thought I needed to actually do the math on this because the publisher did it for me, but they did it wrong. So when you do this on your calculator, let's fix it. It comes out to be 6.97173024. So when you're doing multiplication, division, write down everything that your calculator gives you, at least at the beginning, until you get more comfortable with this. Then what we're going to do to decide how many of those digits we should keep, we're going to look at each of the numbers that was involved in getting that. And we look at 1.052, that one has 4 sig figs. 12.504 has 5 sig figs. And 0.53 has 2 sig figs. The 0 here, we always write the 0 before the decimal point, mostly just to call attention to the decimal point, because decimal points are small and they get overlooked. If a number starts with 0, that's a clue to go look for the decimal point. But this one only has 2 significant figures. So this is the hard part. You have to decide what number is smaller, 4, 5, or 2. 2's the smallest. That's how many sig figs your answer should have. So when we look at this number, we're going to start with this first non-zero digit, and that's 1, and we're going to keep the 9. The 9, that 10th place, is estimated. And then we're going to look at the next digit and decide whether we need to round up or round down. The 7 tells us that this number is closer to 7.0 than it is to 6.9. And so we should record our answer, as 7.0. 2 significant figures. We don't want to call it 7 because that would only have 1 sig fig. Let's look at this one. 2 numbers dividing. Calculator shows you this. You look at the first number, it's got 5 sig figs. The second one has 3. You decide which is the smaller number of sig figs. 3 is smaller. And so then we're going to round this to 3 significant figures. Again, this 0 doesn't count. So we've got 6, 2, 6. 3 sig figs. We look at this number, the first one that we're going to get rid of. It's less than 5, so we round down. And we express our answer as 0.626. Any questions? Adding and subtracting is a little bit different. Here, the result has the same number of decimal places as the quantity with the fewest decimal places. So multiplying and dividing, it's fewest sig figs. Adding and subtracting, fewest decimal places. It can be helpful to draw a line. Stack the numbers up, at least until you get the hang of it. Stack them up like you were going to do addition without your calculator. And then I'm going to look and find which of these columns is the first one where I encounter an estimated digit. In a measurement, it's always the last digit that's estimated, right? So here, the 5 is estimated, the 7, and this 5. So as I go across, here's the 1's place, no estimated digits. The 10th's place, no estimated digits. But in the hundredths, I find an estimated digit. So I'm going to draw a line just to the right of that. So that's where my answer is going to end. This number in the middle has 2 decimal places. The number above has 3 decimal places. This one has 4 decimal places. We're going for fewest decimal places. So do the math, write out the full answer, and then this tells us we have to round it at the 1. We're looking at the 2. It's smaller than 5, so we round it to 5.41. Any questions? Here we have a subtraction. 5.9 minus 0.221. The 9 is estimated, and the 1 is estimated. The 1's place has no estimated digits, but the 10th's place does. So I draw that line. I do the math, I write down the answer, and I'm going to stop right there, just before the line. This time the next digit is 7, so we need to round up, and we get 5.7. Any questions? We're going to get some practice in lab. Some of you, this is just a review. For others of you, you've seen this before, but it didn't make sense then, and it's still not making sense. So what I want for you to do is ask me lots and lots of questions in lab. You're going to work on a worksheet, and there's going to be stuff like this, and you should try it, do your best job, and then come and ask me if you did it correctly, and then we can talk about it. And that's the best way for you to learn. Rounding. We've been doing it, but this is the rules. When you're rounding, if that digit that you're dropping is 4 or less, you round down. If it's 5 or more, you round up. Really important that the magnitude of the number not change significantly when you're rounding it. So let's say, well, this is the example I used yesterday. Maybe it's kind of boring, but whatever. So let's say you have a used car. It's a nice used car that you're selling, and you're asking $12,434 for it. But let's just round it off to the nearest hundred. So we're going to round it to this 4. What I see some students do is they'll round this and say $124. So I'll pay you $124 for your $12,000 car. Does that make good business sense? No. But people do this in chemistry and they don't have a problem with it. What do I need to do to that number to have it keep the same magnitude? I need to put in some place-holding zeros. Now it's 12,400. That's more reasonable. You knocked $34 off the price. You're okay with that. So whenever you are rounding in the tens, the hundreds, the thousands, be careful, because you might make a mistake like this. So the best thing to do is take that number, put it in scientific notation, and then round it, because you won't have to add in place-holding zeros. This is examples of rounding. I'm just going to talk about this one. In the last example, only the first digit being dropped matters. Ignore all the digits to the right of it. So here we're supposed to round to 2 significant figures. So we're keeping that 3 and we're getting rid of what's after it. We're only going to look at the 4. We're not even going to consider the 9. Sometimes students will start at the end and round backwards, and they'll take the 9 and that'll make the 4 round up to a 5, and that'll make the 3 round up, and they'll way more work, and often you get the wrong answer. So just look at the first digit and don't worry about the rest of them. And this came up earlier. In multi-step calculations, only round the final answer. This is another reason why it's good to write down the whole number that your calculator gives you, because you might find that you need it in a future part of that same problem. You don't have to calculate it over again because you've got it written down. You don't necessarily need the whole thing, but I would say carry a minimum of 2 extra digits. So here's an example of multiplication and subtraction kind of mixed together. So we need to find the answer and round it to the correct number of significant figures. What we have to do is we have to consider the result of the subtraction for sig figs separately from multiplying the other numbers, because the rules are different. So when we do this 5.489 minus 5.01, we're going to write down an intermediate value. And then we have to determine where the significant figures are. The rule is number of decimal places for subtracting. This has 3 decimal places. This has 2 decimal places. So this has 2 decimal places. We're not going to actually round it off because that can introduce error into our final result. But what we're going to do is we're going to underline the last significant digit so that when we do the multiplication in the next step, we can count them correctly. So this number has how many significant figures with the underlined one there? 2. That's just got 2 sig figs. The 9 is there because we don't want to have rounding errors. How about this one, 5.903? 4 sig figs. And 6.783. 3. So the smallest is 2. So here's the answer the calculator gives us, and then we need to round it to 2 significant figures, so it ends up being 19. Any questions? Yes?
How is that 260?
If we were doing if we were just doing this problem by itself, 4.89 minus, let me see, 5.489 minus 5.01. What we would do is we would draw a line here, and we would say, oh, this is our last significant figure. And then we would round it off and say it's 0.48. And that would have two significant figures. We're not going to round it, though. We're just going to underline this so that we know, oops, pointing on the wrong thing. Underline this so we know it has two sig figs. And we're going to let those extra digits trail along and round them off at the end. Any other questions? So let's do these real quick. So the first one is just multiplying and dividing. So do the math. And write down the answer. I've got 0.0381443. Anybody else get that? Anybody? No, I'm not sure. That's what I'm asking you. Oh, no. Yeah, I see what happened. I see what happened. I got the decimal before the 9. It is 0.38. See, that's why you do it twice. Okay, so that's the answer. We have just multiplication and division, so we're going to look at how many sig figs in each of these. Which one has the smallest number of sig figs? The last two, actually. This one has 3 sig figs, and this one has 3. So we need to round this to 3 sig figs. So that'll be this guy right here, and our answer is 0.381. Everybody okay with that? This one is adding and subtracting. 0.881. Let's see if I can use my calculator correctly this time. Plus 132.1 minus 12.02. $120.961. Okay. Adding and subtracting, the rule is number of decimal places. So this one has 3 decimal places, 1 decimal place, and 2. The smallest number of decimal places is 1 decimal place, so I round the answer to 1 decimal place. The next digit is 6. That rounds the 9 up to 10. It rounds the 0 up to 1. So this is 121.0. Okay? Because we want 1 decimal place. Sometimes it'll be a 0. That's okay. Here we have multiplication, division, and addition. Let's do the addition and see what we get. 44.11 plus 1.223. So this part is 45.333. That's the whole result. Then we consider the sig figs for the adding part separately from the multiplying and dividing. This number has 2 decimal places. This one has 3 decimal places. So this one has the smallest, the 2. So it has 2 decimal places. How many significant figures does it have then? 4. So this has 4 sig figs. We're going to take this number times that one divided by this one. So let's go ahead and do that. 2.511 times 21.2 divided by 45.333. And we write down what our calculator says, 1.74270399. I think it's better to write down too many digits because you can always go back and cut some off. If you round it off too far and you realize you did it wrong, then you have to do the whole calculation over again. So this one has 4 sig figs, this one has 4, and this one has 5. So our answer should have 4 significant figures. 1, 2, 3, 4 is right there. We look at this guy, 4 or less, we round down, and so this is 1.174. Questions?
On B,
Mhm.
We were to write just 121, no zero, just a solid 121. Would you count that as well?
Yeah, on B, if you wrote 121 without the point 0, and you were being graded on number of significant figures, that would be incorrect. Because that's changing the precision of the result. This is to the nearest 0.1, and without the 0, it's to the nearest 1. So you're losing some precision.
So on C, when you do, so 44.11, that's the fewest decimal places, so that's why you underline that second key,
Yes.
right? And then for the entire problem, you used the fewest sig figs.
Right.
Okay.
The whole problem is this quantity, and so I found out what the quantity was and considered the operation here to find the number of significant figures in there. And then this is multiplication and division. They use the same rules, so I can do the whole thing together. Down here, we've got this number times that number plus this one. So these are in parentheses, so we need to do those first. 12.01 times 0.3. So the result of that is 3.603. We're multiplying, so we're going by number of sig figs. 12.01 has 4 significant figures. 0.3 has 1 significant figure. So this only has 1 significant figure. But we don't want to round it off yet. We're going to wait till the end. So now we're going to take this number that has uncertainty in the ones place, and we're going to add it to this number that has uncertainty in the thousandths, the third decimal place. 3.603 plus 4.811, and that equals 8.414. So here, really, we have 0 decimal places, right? And this one has 3 decimal places. So this is where the book's method of saying number of decimal places is, you can get into a little bit of issue with that. I prefer to think of the uncertainty. This has uncertainty in the third decimal place. That implies that it's plus or minus 0.001. Plus or minus 1 in the uncertain digit. If this is 3.603 with the uncertainty in the ones place, then that's implying plus or minus 1. And so really when you're adding and subtracting, what you're doing is you're looking at the number with the greatest uncertainty. That's what's limiting the answer. This is to the nearest plus or minus 1, so then our answer has to be to the plus or minus 1.
And why is there 4 numbers for the answer? Like, what were you basing that on?
Oh, for this one, 3.603, I wrote down everything my calculator showed me.
No. Okay, so, no, I meant the final answer.
Oh,
So
yeah,
what
I
did you
just rounded it right here. Any questions?
For C, could you explain why you only had or you had 3 instead of, or like the significant numbers, you had 3 decimal places instead of 2? I saw the 21.20.
Okay, because here we're taking this number and we're dividing by that,
Okay, so it's just
and so then it's number of sig figs. And that's something that you really have to puzzle through and do a lot of examples and check your answer on before you can get it straight in your head. That when we're multiplying and dividing, we're counting sig figs, and when we're adding and subtracting, we're looking at decimal places. What's in common is that it's the fewest decimal places, fewest significant figures, but you got to keep track of which one you're doing.